Okay, so now that we've understand conceptually what 2D has to offer, related back to 1D, now that we've gone through sort of the details of the mathematics in the textbook, and understand where that comes from and what that's all about, and see that it's really nothing difficult, it's just complex. So just you have to manage complexity, it's not difficult that you have to manage. And maybe just to highlight what I mean when I talk about complexity and difficulty is like a ball of wool. If I give you a ball of wool and I say to you, please unravel it, anybody can do that. It just takes time. It's not really difficult, it's just complex. But difficulty is something that is to say, let's paint a painting that people would say is good. Yeah, that is something that might be difficult. And so what we're doing in this whole course, everything it's really basic and simple, and every now and then maybe just complex, but nothing is difficult. Okay, so that is important to understand. So let's look at finite element modeling. So I'm going to take you through some basics on finite element modeling. This is just important to understand some aspects so that we really just get comfortable with it. Okay, so first off, I'm going to talk about large translations and large rotations. Let's look at that. What do we expect would happen when I have large translations and when I have large rotations? What do I expect to see? Okay. And then the other aspect is the stress expressed in terms of original geometry. So the stress is always in terms of the original geometry. So if my geometry has large deformations, typically the stress would be different if the cross-section areas are much thinner. But that's the nonlinear effect. In finite elements, we don't take that into consideration. Any deformation is not taken into consideration when you compute the stresses. The stress is always computed in terms of original geometry. So this is what this notebook really just tries to highlight. It's just some basics about 2D FEM. This is also 3D FEM, any FEM actually. But now that we are away from 1D, we can actually ask the questions about large rotations. We saw that there was large translations in the x direction that was part of the shape functions of the 1D element. But now for the first time we can also ask the question about large rotations. That's what 2D offers for us now, for instance. Okay, so here's an element, 2 millimeters by 1 millimeter, Q8 elements of 1, 2, 3, 4, 5, 6, 7, 8, that sort of agreement scheme that we have for the numbering. That's also the same as in the textbook. What we first are going to ask is ourselves, what happens if I take an element and I just translate it into space? What will happen to the element? Well, should we see stresses? No. From a solid mechanics perspective, no stresses should be seen. From a finite element perspective, also, there should be no stresses. If there are stresses, then we should not continue. And then we have a problem. Okay, so let's look at that. I take an element, I put it somewhere here, and I translate it into space. Okay, so that's essentially what happens here. So that's just the Q8 elements that gets translated, and what we can see. So it's a fully, every node's displacement is known. I don't have to solve anything. I just say take the shape functions, take the element expression, multiplied by the known displacements. All the displacements are known because I'm translating each displacement by each point by the same amount. Now we can see what happens. When I look at the von Mises stress, that's just numerical zero essentially. When I look at the sigma xx, that's also numerical zero, because remember, we're working with gigapascal kind of Young's modulus and stuff like that. So 10 to the power of 9 kind of order of magnitude stuff, or actually 10 to the order 11 magnitude stuff. So then a 0.0015 is essentially 0. Okay, so that's just important to understand that you interpret this numerically. So it's about the range of the numbers. What's the largest number that you're working with? If that is 2 to the 11, then anything less than, let's say, 0.01 is going to be 0 numerically. Okay, just to give you a gut feeling more or less. Okay, because typically we have about 12, 13, 14 digits depending on what kind of precision happens inside this. So, but this is numerically 0. Sigma xx, sigma xy, yy also numerically 0. Sigma xy numerically 0. Okay, because this number in context of a number that was 2 to the 11 in that stiffness matrix. So this we can see works fine as expected. Okay, as advertised. No stresses when I have a rigid body translation. Next question: what would happen if I have a rigid body rotation? Okay, is my expectation, what's my expectation from the solid mechanics point of view for my theory? Because remember, we do linear elasticity. When we had angles, did we do any simplification with them at any point? Yes, we did. We made all those tan angles, gamma, the angles that were tans and stuff like that, or cosines and sines. We simplified all of them, yeah, and we linearized them. So the reality is, if I take an element and I rotate it, large rotation, I would expect no significant stresses for very small rotations, but as soon as my rotations go large, I expect things to go haywire. And the reason is because we're busy with linear elasticity. So this is from the solid mechanics perspective. From our theory, my expectation would be that we won't be able to see, we will see significant stresses for large rotations. And that is just based on the theory that we're using. So let's see for ourselves if that's the case. And our finite element is just essentially an approximation of that. So let's see what happens if we have large rotation. So here's essentially a patch. That's that. There is essentially rotation. Okay. So again, let's just talk about this quickly. From my expectation, if I have this in real life, there should be no stress. Okay. Doesn't matter how large the rotation is. It's a reduced body rotation. So my expectation from real life, from physical reality, is no stress. Now we have a theory that we're building, linear elasticity. Because we've linearized the angles, remember that from the derivations of the shear strength and stuff like that. Because we linearized the angles, essentially also remember from that we had that decomposition of the strain matrix. We had essentially the skew component and the symmetrical component. We only used the symmetrical. We threw the skew component away. That skew component is actually a rotational component that we threw away. So we essentially threw it away. We claimed it's zero. Okay, when we threw it away. So essentially we forced it to be zero. So that's essentially what happened on that side. So there's a couple of places that hints to us that we've simplified things. Okay, but the bottom line is, from the linear elastic point of view, my expectation is 100% that this should not give me zero stresses. Okay, that there should be some stresses. How significant? I don't know. Let's see. We can go and actually work it out. But we're going to compute it down numerically to see for ourselves what those stresses are. But this is an important consideration from a modeling point of view. If you have any problem with large rotations, let's look at the stresses and see if they're significant or not. And then you make a call whether what you do here. But let's first look at the results and then we interpret it. Okay, so here again, we are running a finite element program. I'll talk about it now. I just first want to just go through this basics, and then we can start opening up this program and unmantling that. So when I look at the meter stress, I see there's 2.28 times 10 to the power 4. Okay, so that is not a small stress. That's already something significant. Okay, that's definitely not zero. Again, the small numbers plus. There's a plus there. That's the number essentially there. So that's what we have there is a 2.28 times 10 to the power 4 Pascal. Okay, when we look at the sigma xx, similar order of magnitude, sigma yy, similar order of magnitude, shear, essentially the shear component looks like it's quite small. Okay, that's essentially zero. But these other components, the normal, the sigma xx and sigma yy is definitely not zero. Okay, so you can see there how those components affect it. So there is significant stresses that form when we have large rotations. So the reality is, when you have a problem with large rotations and you need to model it with finite elements, you cannot use linear elasticity. No go. You have to go for a nonlinear model. And it's called geometrically nonlinear model, so that you can handle the large rotations. This is really important aspect to understand. So you need to understand the limitations from the solid mechanics theory that we've applied, which is